Okay, hi everyone. So this lesson is about the sun and why the earth experiences seasons. So let's at the outset consider this question. What is the major cause of the differences in the seasons? This is the big question for this lecture. So is it that the earth is closer to the sun in the summertime? The earth is moving faster in the winter? Earth's axis is tilted, or were the seasons just invented by Hallmark to sell cards? So keep this question in mind as we go through the slides. All right, thinking about the seasons and understanding why we have them requires an understanding of the shape of the Earth. A lot of people are taught that everyone thought the Earth was flat before Christopher Columbus sailed across the ocean, but that's not true. Humans have known that the Earth is round for a long time. In fact, there are two examples of scholars coming to this conclusion independently. So one was Eratosthenes in Greece around 240 BCE, and the other is Aryabhata in India around 500 CE. So this is Eratosthenes, this is Aryabhata. So each figured out a deceptively simple but kind of ingenious way to measure the circumference of the Earth. They realized that if you knew the distance between two cities, you could estimate the circumference of the Earth by kind of sticking a stick in the ground at each city and measuring the length of the shadow that that stick casts at the same time on the equinox. So it looks a little bit like this, right? So we have a stick at this location and then a same size stick at another location. If the Earth is round, we would expect that a stick planted into the ground closer to the equator would have a shorter shadow compared to a stick planted on the ground or in the ground at a higher latitude because of the angle of the sun's rays. So right here, we have this stick right here. It's really not casting a shadow at all. The sun's rays are coming directly on top. This one here, though, the sun's rays are coming in more at an angle and it's creating this longer shadow. So both Eratosthenes and Aryabhata used this method to estimate the size of the Earth. And they actually came pretty close. You can use some trigonometry to work this out. So these are just two people in history that we know figured this out. But I think it's important to note that because we know that these two people figured out independently, that it's very likely that others figured it out too, but just didn't write it down or were kind of otherwise lost to history. But the point is that it has been known for a couple of thousand years at this point that the Earth is really more or less a sphere. So we live on this ball and it goes through a couple of basic motions that all planets go through, right? It's rotation and revolution. So rotation is just spinning on its axis. So one rotation equals 1 day, right? About 24 hours. Earth's rotation gives us the difference between night and day. A revolution is the time it takes Earth to make one full trip around the sun. So we call that a year, right? So here we have an example, just a diagram of the rotation of the Earth. And down here is a little schematic of how the Earth goes around the sun, but also spins itself. I want to note something about Earth's axis, right? This invisible pole on which the Earth spins. So it is tilted, right? It's tilted 23.5 degrees. And this tilt is oriented the same way, regardless of where Earth is in its orbit around the sun. So you see here at point 1, we have the axis tilted this way, and it's pointed in the same direction, regardless of where it is, right? The direction the axis is pointed doesn't change. So this combination of two movements, right, the rotation and revolution, results in something called the sidereal day. So if you were to go out and measure the exact location of the sun in the sky at the same time each day, you'd find that the sun is in a different place. The sidereal day is the time it takes for the sun to return to the same apparent location in the sky, and it's about 4 minutes shorter than our standard 24-hour rotation period. If you were to go out and take a picture of the sun at the same time each day, you'd find the sun makes this kind of like oblong figure eight or kind of infinity symbol, right? And that's because of the combined effect of the rotation of the Earth and its revolution, and it's called an analemma. It's the path the sun takes throughout the year. I'll talk more about that in a few minutes, though. Okay, so I've talked so far a lot about Earth's rotation, its revolution, and its tilts, but what does this actually have to do with the seasons? So it is a common misconception that it's our distance from the sun that causes summer and winter. And while it is true that Earth's orbit is not a perfect circle, and that sometimes we are slightly closer to the sun than other times, that's not the cause of the seasons. And we know this by taking a look at Australia. So think about Christmas in Australia. They still celebrate Christmas on December 25th, which for us here in Albany is pretty chilly, pretty cold, might be pretty snowy. But for Australia, this is a balmy summer day. But we are on the same planet, right? So if the distance from the sun was causing the seasons, we would expect everyone to experience winter at the same time. But that is not what happens. So what is happening? So let's think about ways that we kind of classify summer and winter. So maybe we think about temperature, right? Warmer weather versus colder weather. Summer is generally warmer than winter. We might have some warm winter days, but on average, it's much cooler than the summer. Maybe we talk about the length of the day, right? Summer days are longer than winter ones. We can also think about what is actually happening at the North and South poles. And examining what's happening at the North and South poles is actually really informative. So let's take a look at this diagram of the Earth at different locations in its orbit. They represent the seasons, summer, fall, winter, and spring. Notice that at each location, the Earth is tilted in that same direction, right? I also want to draw your attention just briefly to this dividing line right here. Each of the planets have it. This is the dividing line between night and day. It's called the terminator. I don't know why, it just is. Okay, so let's look real quickly at the North Pole over here. So the North Pole is completely on the daylight side of the terminator. When the Earth is in this location, the sun never sets at the North Pole. You get this phenomenon called the midnight sun. You can also tell that the Earth is tilted towards the sun, so the sun's rays are hitting it more directly, right? In the southern hemisphere, the rays are a little more spread out. It's not as direct. On the other side of the sun here, you can see that the North Pole is totally on the night side of the terminator, which means that the sun will actually never rise. And because the axis is tilted, the sun's rays don't hit as directly as they would as if they were over here. So right here, we see the North Pole totally sunlit, right, on this side of the terminator. Over here, the North Pole is totally, it's in the dark. The sun is not hitting it at all. So which one of these Earths represents summer and which represents winter? So the Earth with more direct rays will absorb heat, more heat and be warmer. So that is the summer location for the northern hemisphere. I will get caught doing this throughout this section. This is Northern Hemisphere summer. And so over here, this is Northern Hemisphere winter. And from there, it can be straightforward to figure out exactly what the other seasons are. So summer, autumn, winter, and spring. Then we start over again. And remember, this will be the opposite in the Southern Hemisphere. So in the Southern Hemisphere, over here would be winter, and this would be summer. There are a couple more things I want to mention about the sun and its path in the sky. So as the year goes on, the sun's path across the sky will appear to change. So on the first day of spring or the first day of fall, we have something called the equinox. And so the sun will take this path over the sky. This is its equinox path. So let's say we're in the first day of spring. So every day after the first day of spring, after the spring equinox, the sun will creep up, up, and up until we hit, for the Northern Hemisphere, the longest day of the year. That is the June solstice. And when it takes this path, this is the highest path that the sun can take. After the June solstice, the sun will creep back down to the equinox path to the first day of fall, and then it will go down even more to the December solstice, which is the shortest day of the year, and it is the lowest path the sun can take in the sky. So the path of the June solstice it's separated from the equinox by 23.5 degrees. And the equinox is separated from the December solstice by 23.5 degrees. Dr. Hassel has made a nice demo video that is also uploaded on Canvas, and I suggest you take a look at that before you do the sun simulation activity. All right, so knowing this, the analemma might make a little more sense, right? It's a figure 8 shape that the sun makes if you take a picture of that location at the same time throughout the year. So the analemma is oblong because the Earth is tilted, and it's a figure 8. It's a lopsided figure 8 because the Earth's orbit is a little eccentric, meaning it's not a perfect circle. It's ever so slightly egg-shaped. And this means that sometimes the Earth is closer to the sun than other times, and that causes one of the lobes to be bigger than the other. Okay, so hopefully now we can come back to our initial question of what is the major cause of the seasons? And you now understand that the answer must be C, because the Earth's axis is tilted, right? Sunlight will hit some regions more directly than at other times, causing these cycles of cold and warm weather. But I think that's it for this lecture. Again, check out the demos available on Canvas and let me know if you have any difficulties or if you have any questions.